Okay, so we're very happy to have Andy Strominger speaking to us next, all the way from Texas, where he will write on a nice whiteboard. Thank you so much, Andy, for speaking here remotely. So go ahead.
Okay, great to be here in Switzerland. So I am going to talk about some work on the problem of celestial amplitudes and more generally the symmetries of nature. I'm going to give a brief sort of 5-minute motivational introduction review, and then I'm going to skydive into some very recent results, but I'll try to present them in a way that's more generally accessible, because I don't think there are too many experts on this subject in the audience. So the basic idea is we want to talk about a new way of representing the S matrix for scattering in 4-dimensional asymptotically flat space. And so ordinarily, this is a picture of Minkowski space. And ordinarily, we would send particles in from scribe minus. We draw a picture like this, and there'd be some interaction region. And in this picture here, we represent it all in terms of a sphere at infinity, and we just mark the locations of the in and outgoing points. So there's nothing really deep about this. And in fact, it was talked about by Dirac a long time ago in the 30s. It's just a different picture, a different representation of scattering amplitudes. And in particular, when one does this, it's very useful to go to a conformal basis. Here we usually work in plane wave states, in which everything is an eigenstate of the translation operator. Here we use states which are, transform representations of the Lorentz group, which is SL2C. It acts as the conformal group of this two-sphere, which is really living up here at infinity. And one of the things we've learned in the last 5 or 10 years is that these S matrix elements, rewritten as correlation functions, transform not just under the finite dimensional conformal group of the sphere, but when quantum gravity is included, soft theorems imply that they transform under the whole infinite dimensional group. So we can exploit the powerful methods that have been developed in 2-dimensional conformal field theory, though we have to be careful when doing so, because some of the properties of this collection of correlators are not the ones we usually assume in 2-dimensional conformal field theory, like, for example, unitarity, and other questions like locality and so on are not fully understood. Now, what do we want to use this for? Well, one very important question that we amazingly don't know the answer to is that this formalism we think is very useful for getting is, what are the non-trivial symmetries of nature that in the approximation where space-time is asymptotically flat? And by non-trivial, I mean ones that are associated with conservation laws that can be measured. Now, 100 years ago, the answer to this question would have been energy, momentum, maybe a few more. And then 50 years after that, BMS came along and they told us, no, in general relativity, you don't get the Poincare group out of diffeomorphisms. It's something more complicated. But they didn't actually tell us what the answers were, what the conserved quantities were. Now we understand that there are infinitely many conserved quantities. They involve moments of incoming energy flux and displacements caused by the memory effect. So to measure these conservation laws, you would need both calorimeters and energy machines, and memory measurement devices, which of course is very hard to measure, but in principle possible. So, by so we would like to answer the question, what are all the laws, what are all the non-trivial symmetries and associated conservation laws of, not of string theory, but of the laws of physics that we've already experimentally verified, like physics and the standard model. And that's a question the experiments have already done. That's a question for theorists, and it's a question we haven't answered yet. Also, finding all the symmetries is step 0 in constructing some holographic representation of quantum gravity in asymptotically flat space. It's certainly was the first step in the famous ADS-C correspondence. Now, just one more thing I want to say is if you have a momentum here of particle P, this sphere, we put a coordinate Z on it, and Z is equal to P1 plus I P2 over P0 minus P3. So this coordinate Z on the coordinate on the celestial sphere can be thought of as being constructed in the standard way from these from the momenta of the particles that are scattering. Now, transforming the momentum space scattering amplitudes to the ones on the celestial sphere, there's a whole industry of that, and there are a lot of intricate and beautiful mathematical details. I'm not going to go through that. I'm just going to start with an interesting formula. And the formula is going to be for the operator product expansion, where you have two gluons which come out very near at very nearby points on the sphere at null infinity. And of course, there has been a subject of collinear singularities in ordinary quantum field theory. What happens when two gluons become collinear? So in a sense, we're translating that subject into a thing where if you solve that problem completely, then you would have solved the problem of finding all the operator product expansions of the primary operators that live on the celestial sphere. So let me just, that formula has been computed. And I'm just going to write that formula down. And it's been computed in a number of different ways in different papers. It can actually just be computed by symmetry. It can be computed by Mellon transforming the known results. But let me just write it down and explain it without deriving it. So I'm only going to talk about positive helicity gluons in this talk. And that's not because negative helicity gluons aren't interesting. It's because when positive and negative helicity particles start interacting, life becomes complicated, and we haven't understood yet how to characterize their interactions. So, though we can write down these operator product expansions. So let's say we have one positive helicity gluon, and I'm going to put O as the operator, which acts at a point on the celestial sphere. And I'm going to have it have conformal weight delta 1. And it emerges at a point Z1, Z1 bar. And I'm going to take that to be near a second positive helicity gluon of weight delta 2, which is emerges at a point Z2, Z2 bar. And this operator product expansion, we first of all get a minus I F A B C OC of Z2 Z bar 2 at with conformal weight delta 1 plus delta 2 minus 1 divided by Z1 2. And the whole thing is multiplied, there's a coefficient here, times the Euler beta function, which is delta 1 minus 1, delta 2 minus 1. That's it. Sorry, that's it. And for those of you who don't remember, the beta function of x and y is equal to the gamma function of x, gamma of y over gamma of x plus y. Okay, so this says if we put in two gluons, positive helicity gluons with these conformal weights, they have an operator product expansion on the sphere, which could be thought of as a transform of the collinear expansion, which says that they will make a third, and of course there's plus dot 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 dot, it's an OPE, a third one whose conformal weight differs by this, and this is the OPE coefficient, is the Euler beta function. Okay, so that's the basic formula, the sort of starting point that I have to grab out of the literature. Let me ask, first of all, can everybody see the screen?
Yeah, we can see the screen okay. Yeah.
Okay.
Just make sure that sometimes you don't always stand in front of it, but we see it pretty well.
Okay. All right. And are there any questions about this formula? Okay. So now, one of the important parts of this formula that it is going to drive this whole discussion is that it has poles. Let's, in particular, we think about poles where the conformal weight, delta 1, goes to any integer 1 or less. So 1, 0, -1, -2, etc. And we want to understand what goes on at those poles. So let's define an operator. Let's first consider the first one, where delta 1 goes to 1. And let's define R1 A of z is equal to the limit as delta 1 goes to 1, delta 1 minus 1, O delta 1 of z bar plus A. And these are positive helicity guys. So now it would seem like this would be 0 because we're taking the limit as delta 1 goes to 1 and multiplying by delta 1 minus 1, but it isn't because this OPE here has a pole in it. So this factor is designed just exactly to kill that pole. In fact, we could also, there's another representation for it as a residue around the pole. And so this thing, we can't ignore this operator because it doesn't decouple from the operator product expansion. Ultimately, we hope to find some complete set of operators which closes under the operator product expansion and even better factorizes on conformal blocks, but I'm not talking about that today. Okay, so that's a finite operator. In fact, in that case, the dimension of this operator becomes 1, 0. So the dimension here would be H bar, sorry. The fact that these are positive helicity means they have spin 1, so I really should have written this up here. I would have H bar equals delta 1 plus 1 over 2, delta 1 minus 1 over 2. So R is a 1, 0 operator, and it has to be holomorphic. You can see that in many different ways. It essentially is equivalent to the conformally soft theorem, or you can just may seem obvious that a dimension 1, 0 operator will always have to be holomorphic. And so its operator product expansion looks like R plus A 1 of Z with an arbitrary O plus B of, let's call it Z1, O plus B of an arbitrary delta 2 of Z2, Z2 bar goes like 1 IFABC over Z1, 2. And this beta function just collapses to 1, O plus C, Z2, Z2 bar. Okay, so this generates all the symmetries associated with this leading soft theorem, the leading soft gluon theorem. And I'm talking about tree level here. Or we could also be doing photons, and these could be charged particles. This is a holomorphic current. We can integrate by arbitrary functions of Z, holomorphic functions of Z. We can integrate it around various contours, and we can get infinitely many Ward identities. Those infinitely many Ward identities of this, it's an SU2 current. If this is a group G, it's a G Kac-Moody current algebra, and it generates all kinds of symmetries of these correlation functions. And since the correlation functions are a representation of scattering elements in space-time, it's also generating symmetries of space-time scattering elements. Okay, now.
One quick question, Andy.
Yeah.
On the right-hand side, that have the same, that has the label delta 2, same as the one on the left, or it's a different?
Sorry, delta 2, yeah. Because it's delta 1 plus delta 2 minus 1, and we're letting delta 1 go to 1. Thank you.
Okay, thanks.
So it maps the operators back into itself. This is the only ones that maps the operators back into this itself. There are going to be more, and they're going to shift the conformal wave. So let's look at that.
So does that R operator then sit in the OPE of O delta 2 with itself?
It could if the delta 2 were in integers.
I see.
Okay, so we could now instead, so there's a whole tower of poles here, you see? And so the next one, let's call it R0Z. And now we're going to take delta 1 to 0, and we're just going to multiply by delta 1. And what does that do? Well, since this thing has delta equals 0, it has sort of H equals plus a half, and H bar equals minus a half. And so we want to define now the limit. So now we're coming into these odd negative dimensional representations. But all we're doing here is we're about to study, we just talked about the leading soft theorem. We're now studying the subleading soft theorem. And that was discovered by Francis Lowe in 1958. So the use of these, it is an operator with negative dimension, and it has various properties when you insert it in the S matrix element. Okay, so this has a doublet representation. This H is the right moving conformal symmetry, and we've got a negative dimension representation here. And so there is a doublet. When you have negative dimension representation, there's a doublet that appears, a finite dimensional doublet that appears. And so we want to take the limit as delta goes to 0 of delta O plus A delta and we want to expand it as, well, it's a function of z and z bar. Has to depend on z bar because it's in a doublet. So we want to define the expansion a little bit differently now. Square root of z bar, RA minus a half, plus, and let me put a 0 here because it's associated with the dimension 0 guy, plus RA 0 plus a half, 1 over square root of z bar. Okay, so it had been noticed previously that that there were really two subleading soft theorems. They were in a doublet. It wasn't really understood how they were related, but now we see that they're simply in an SL2R doublet. And again, this O depends on Z bar, but when we do this finite dimensional left mode expansion, we get a bunch of holomorphic currents that transform in some finite dimensional representation of SL2 R bar. So continuingly, now we can't stop here. And we can't stop here. And this was has been noticed by many people in the years, Hamada, Shu, Bovara, Lin, Zhang, and even before that, people talked about it. These soft insertions don't commute with each other, and they generate an infinite tower of symmetries. And so the question I'm interested in is, what are these infinite tower of symmetries? How do we organize them? Apparently, they're symmetries of nature. What are they? And but once you have this formula for the operator product expansion, which is all operators, soft or not, it's not that much work. It's a little bit tedious, but it's not that much work to look at the operators associated with every pole here and compute their symmetry algebra. And that's what we did. So we more generally defined it at level K. We took the limit as epsilon goes to 0 of O plus A epsilon plus K ZZ bar. And we write it as the sum n equals K minus 1 over 2, 1 minus K over 2, R K A N of Z, a holomorphic thing. And then we have this finite expansion, Z bar N plus K minus 1 over 2. So as you go to deeper and deeper poles, they live in larger and larger SL2 right multiplets. And K runs from 1, 0, minus 1, minus 2, infinity. Okay, so we have an infinite tower of soft theorems. And what are they? Okay, so the next thing we did was we take all these R's, we use this formula, and we can compute an algebra.
Oh, one quick question, Andy. So the same K and different N, they have different weights, I guess, right?
Right. K is the total weight. H plus H bar.
Okay, good. And N is kind of the difference of the left and right or something? Or?
N is essentially N runs over different values. N runs over I guess 2K values, something like that, or just K values, K plus 1 values. n runs over k plus 1 values. And so they sit in a representation in the SL to our right, which is the holomorphic symmetry we're ignoring. The SL2K our right, that gets bigger and bigger as you go further and further down the ladder.
I see. Okay, thank you.
Okay, so all of these operators they're all soft operators. They all create symmetries of S matrix elements. All of them would have observable memory type effects, conservation laws. They're real symmetries of nature. As we'll see in a moment, after the second one, it turns out that commutators of the second one produce all higher ones. So they're not new constraints on the S matrix. If the S matrix satisfies the conservation laws associated with the first two, or in gravity, the first three, then all the rest of the conservation laws are automatically automatically satisfied. Okay, let me now so you can work out from the operator product expansion, if we define A commutator B of Z as 1 over 2 pi I, the contour integral of Z, let's make this dW around Z, A of W, B of Z. So when you have two operators who OPEs make a pole in the stupid obvious way, you can define a commutator. So so that gives us a commutator, and we can define the commutator of all these R's. And these formulas get pretty long, and so I'm only going to write one just to give you a flavor. So this is this infinite tower where KL runs from 1 to minus infinity, and N and M are bounded by K and L. It's equal to minus I FABC 1 minus K over 2 plus 1 minus L over 2 minus N minus M factorial over 1 minus K over 2 plus N factorial 1 minus K over 2 minus L over 2 plus M factorial, and then minus the same thing with N goes to minus N, M goes to minus M. So it's a complicated expression involving 6 different factorials, and then it multiplies RK plus L minus 1 comma C, N plus N. So this is an algebra. It's the algebra of all the higher soft current. It obeys the Jacobi identity. We're going to find a much simpler form of it by doing a light transform in a moment, so I won't discuss it further. What I'm going to do instead is I'm going to go on to gravity, where there's a very similar story. Okay, so in gravity, you have a similar story.
Just to let you know, the timing of the talk is about 5-10 minutes left.
Okay, great.
Yeah.
In gravity, there's a similar story where we have fields called G. And again, their OPEs, the structure is a little bit different. It's all worked out in great detail in the literature. And I'm going to find the analog of the R's, which are the H's, which are the limit as epsilon goes to 0, epsilon, G plus K plus epsilon. And we're going to define that as sum n equals k minus 2 over 2 to 2 minus k over 2, hkn of z, z to the n plus k minus 2 over 2. So we're going to use the same z bar. We're going to use the same trick where we're going to look at all the operators that would be zero, all the operators that have poles in their OPEs at what conformal weights. We're going to rescale them so that they hang in. And then we're going to take them and we're going to expand them in z bar. And we're going to be left with these multiplets, these growing multiplets. And now k runs from 2 down to minus infinity. And they also have a complicated algebra. And now comes the magic trick. And the magic trick is we define WPN is equal to 1 over kappa, Newton's constant, which came into the OPE for the graviton, gamma P minus n, gamma P plus n, Hn minus 2p plus 4. And when we do that, something very nice happens. Now, let me just say, this is basically, a light transform is a subtle thing. People use light transforms in different ways, but this is basically what I've done here is a light transform on the z-bar side, but a finite dimensional version of it with these finite dimensional representations. And I find, lo and behold, that the algebra just collapses down to WPM, WQN, MQ minus 1 minus N, P minus 1, W M plus N, P plus Q minus 2. So this is the algebra of positive helicity generators of soft symmetries in gravity. And I want to stress here that I'm talking about every theory of gravity at tree level. String theory, twistor theory, anything. I haven't assumed any microscopics. And this very complicated algebra telescopes down to the W algebra. Now, this is called the W algebra. It's a higher spin algebra. That's, I think, the first place that I know of that it appears. Now, okay, first of all, now M, so now K was restricted, but now P runs over 1, 3 halves, runs over half integers greater than 1, and 1 minus P is less than M is less than P. Okay, so this is actually a Kac-Moody algebra whose group is, because of this restriction, is a wedge algebra of W1 plus infinity. And it's 1 plus infinity because P starts at 1. And it's a Kac-Moody algebra because each one of these things, they came from the H's, and everybody depends on Z. So this is a current algebra. Now, precisely this current algebra, it's a mouthful, so people usually just call it W algebra, but precisely this current algebra, the Kac-Moody algebra of the wedge algebra of W1 plus infinity, has appeared repeatedly over the last 50 years. The first time that I know of that it appeared is in the 60s, before it was named. In the 60s, in the Penrose construction of the nonlinear gravitons using twistor theory. And in fact, this algebra is sort of the basic of twistor. When they say W1 plus infinity in twistor theory, they mean this Kac-Moody algebra of the wedge algebra of W1 plus infinity. It's appeared in string theory. It's Klebanov and Polyakov wrote a paper about discrete states of C equals 1 string theory generate this loop algebra. Pope and Shen wrote a series of beautiful papers in the early 90s about this group, and also what looks to me, though it hasn't found a place yet in modern work, it looks to me like they found a deformation of the theory that's much more non-trivial, but very highly constrained, a sort of quantum version of the theory that could also play a role. So 4 good things have happened all at once with this weird definition. And let me just also say, without writing it out, because I guess I'm probably running out of time, that there's a similar definition of the R's. I will write it out. There's a similar definition of the R's, and that complicated R algebra in terms of some S's becomes SQM A SPBN equals minus I FABC SQ plus P minus 1 comma C M plus N. So the whole tower, and this also transforms irreducibly under the W's. So the whole tower, the whole infinite tower of soft gluon symmetries organizes itself into an irreducible representation of this W1 infinity. And of course, the soft graviton symmetries are an adjoint representation of that symmetry. So 4 good things happened all at once. A rather complicated algebra, which, by the way, I worked out with Guevara, Imwich, and Pate. Telescoped into this very simple and familiar expression. The other interesting thing is the negative weights that appear in the earlier representation, which correspond to transformations under some other SL2R, have disappeared. We'll have only positive weights here. So that's a nice thing. Also, I won't comment very much on this, but there's been some papers from the twistor people at Oxford recently, particularly Sharma, that this is what I've done here is the sort of half twistor in some other language. It's the half Fourier transform, half twistor transform that Witten did in his early papers on perturbative twistor theory and the perturbative spring. And it's a procedure that the twistor people already found, had already used and found very natural. And moreover, if you do these half Fourier transforms, which are like light transforms are the half Fourier transforms that the twistor people do, you find that the scattering amplitudes, and this is something I haven't discussed, the scattering amplitudes in momentum space have 4 delta function singularities. All scattering amplitudes in momentum space are either 0 or infinity to the 4th. But here it would be nice, whereas in conformal field theory, we're used to smooth scattering amplitudes that aren't distributional. And previous work had eliminated 3 of the 4 distributions out of the 4-point function, but there was still some delta function left in the 4-point function. And when you go to these half transforms, that delta function disappears, and we can study smooth objects. But most of all, I think that it's exciting that W1 plus infinity, which had appeared frequently, but always in the context of sort of simple integrable systems, we're now discovering is actually a symmetry group in the real world, albeit an approximation to the real world, in which space-time is asymptotically flat, and we're neglecting quantum corrections, though it may well get preserved. Some part of it may survive quantum corrections, as soft theorems tend to do. We're studying that now, but it's anyway. It's this symmetry algebra is arising in a corner of the real world, which is certainly not a special integrable system. So right now we're studying. We are studying the problem of quantum corrections, and there's some nice places to study that. A natural arena for developing these ideas is self-dual gravity, which also has a string theory representation, and that might be sort of a good toy model for celestial holography. But let me, I guess I'm out of time, or do I still have 4 minutes?
No, no, you're out of time. If we have.
Okay. All right, out of time. Oh yeah, I'm sorry, I was supposed to stop. Okay, yeah.
Well, that's okay.
Thank you.
First, let's thank Andy again for a wonderful talk. In view of the time, we have time maybe for one brief question, if there's one, either from the in-person or remote audience. Yeah. Well, maybe I'll ask you then. Do you expect these symmetries will persist at loop level? Or does it matter? Or
well, they may. So right now we're studying the simplest kind of loop corrections, which are the all plus amplitudes. You know, we haven't written the paper up yet, but it looks like, so in both gravity and in Yang-Mills theory, self-dual gravity, self-dual Yang-Mills theory, the all plus amplitudes have been explicitly computed, and it looks actually like the symmetry algebra is completely undeformed. Certainly there, and we think it's undeformed. So in that context, it persists. That's sort of the simplest context. You only need to understand the leading and the subleading soft theorem, because if they're preserved, the whole tower is preserved because they're generated.
I see. Mm-hmm.
And it's known that the subleading soft theorem has corrections from some short but finite list of low dimension operators, up to 6 or something. In QED, it's deformed by, psi bar f mu nu, gamma mu nu psi. And so there aren't many operators that can deform it. If they do deform it, they don't eliminate it. There's still a symmetry. And so it would seem that the symmetry can't be eliminated. Maybe it can be deformed. I should add that the dimensions that are made by So that also for the gravity, there's a short list of higher dimension operators that can deform the symmetry, but they all have the property that they couple things of opposite helicity. So those deformations don't affect the algebra of positive helicity soft theorems, and right, they don't affect the algebra of positive helicity soft theorems. So it's a very highly constrained problem. I think something interesting will happen. I think we can control it, but I don't know exactly how it's going to come out.
Thanks. So in view of the time, let's thank Andy again for a nice talk.
Thank you.